Now, there's no way that I can discuss all of these students or all of these projects, but at this point I would like to introduce a new unit after having heard Phil's talk, Kronberg. I'd like to talk about the Millie Kronberg, and I would say that some of these projects are up into the hundreds of Millie Kronbergs, asymptotically approaching a Kronberg. Anyway, I'm going to concentrate on these 6. Now, when I wanted to start here, Fred said, "Are you sure you want to talk about that?" And in fact, yes, because this is supposed to be the collaboration between our group at U of A in electrical engineering and Hertzberg Institute, which is meant primarily DRAO. And yes, very much because this is the way we started. Okay, this is 7 Mile Flat, which is directly west, I'll show you on a map, of Innisfail in Alberta. This is Corkscrew Mountain, there's the road. That way east lies civilization. There's no electrical power here, and it's a 4-hour drive to Edmonton. 400 kilometers this way is Penticton. Why are we out there? John Galt, okay, these are the existing decametric arrays that Rob was talking about. John Galt would like very much to have a larger array, also decametric, with a beam comparable to what the 26 meter has at H1 line, right? So it scales to about this size. He asked people in our department to find a potential site. So here there's Edmonton, Red Deer, Innisfail. It's a site on the Clearwater River on provincial land. So what to do? It looks like there's a usable band in a marine mobile allocation. Thing to do is do some interferometry. So here's a corner reflector. That's a wire screen. There's a wire ground plane, a folded dipole. We built a half-mile interferometer, and we built a 3-mile interferometer. We are here in time at Solar Max, heading into Solar Min. So John would like very much if this project got underway and the T got built by Solar Min, right? The Canadian astronomical community has its sights set on something else. In '74, the CFHT agreement is signed. This project goes nowhere. But some things did come out of it. So a very capable student, Brian Casper, has an idea. He realizes the importance of man-made interference. He has the idea of forming with a cross-power digital circuit, whatever, 128 channels. So he figures, why not excise the man-made interference from as many channels as you have to? And here's an example where he's excising about 30% of them, and it does work. He also comes here, incidentally, our first pilgrim. Meanwhile, here, of course, the emphasis is changing to centimeter wavelengths. Right, so the synthesis telescope at that time looks like this: 2 antennas, 300-meter baseline, capable of this kind of imaging. And this supernova remnant is DA 530, and you'll see it again. Right, so the next thing that happens is Fred Vandeldik comes here on a sabbatical. Fred, Tom, right? So Fred is working with Tom Landecker, and the objective is to slave the VCO, which is the LO system, whatever, to a master here. And what they have is buried cables, and therein lies the problem. The cables have about 3 microseconds delay. So you would like to control the phase of the LO very, very accurately, despite instability. And to Fred, it's trivial, maybe, but to me, control systems are very difficult. They do achieve stability, they do achieve accuracy, and it works. Meanwhile, of course, the 30 megahertz IF comes back to the correlator in the second cable. Oh, the problem being that cable length changes with temperature. Right. In 82, I should probably say 81, the synthesis telescope has changed to this 600 meters baseline, 1 arc-minute synthesized beam, etc. Still operating at 1420. And as I forget who said earlier, the desire is to go to high resolution imaging at a lower frequency. We just heard from Tony at 610, 16 arc-minute beam. If you ask for high-resolution imaging at this time, it does not exist. Well, it does. Westerbork, for example, he just said, produced high-resolution images, but it does not include the low-order Fourier components. There is a really good survey by Haslam with the Jodrell Bank telescope with about 45 arc-minutes resolution, which is there for the low-order spacings available. Hence, Tom, etc., say, let's go to 408 and build a 408 system on top of the existing 1420. Right. We get a really, really good student named Wing-Fi Lo. He says, here is a conventional interferometer with 2 correlators, one producing the real channel of quadrature of output, the other producing quadrature output, which requires a broadband 90-degree phase shift. And at any instant, you have to compensate for the geometrical delay. He realizes, though, that you can do this digitally. Why not? Digitally and in software, if possible. And he recognizes, his supervisor is Peter Dudney. I'm not sure whose idea it was. I think it was Wing Lo's idea. This can be implemented as a Hilbert transform in software. Right, so here's what he's planning to do. Anything in a red box is in software. This other stuff is all digital hardware, right? So he forms first the in-phase cross correlation function at 16 values of delay, 1/16th of a microsecond intervals, interpolates to the required value of tau, and there's your in-phase output. Now for the quadrature channel. You have to do the Hilbert transform at that value of tau. That's a single value of tau. So the HT becomes or degenerates into a dot product. Quick. And there's what he comes up with, a single bay of equipment capable of handling 10 interferometers. Right, it's going to work. And what's available is a new microprocessor, 16-bit, which is very fast, etc. But there's no operating system. He has to write what he called a tiny operating system, but he writes it in a very buggy, Gary was just telling me, a very buggy version of C. Nevertheless, he makes it work, various workarounds and so forth. Right, it does these things. There's another half of the project, however, the analog side. So the feeds at 1420 are working, but they have to be modified to include 408. Also, there's requirement for the LO system. Right, so he's got 2 subparts to this project. Who? Bruce Veit, who's here. Okay, his supervisor is Tom Landecker. I'm not sure who has the idea, regardless. They're going to replace the existing rectangular feeds with these circular feeds. Bruce adds an additional choke ring, optimizes the feed for 1420. I forgot to tell you, the golden rule is thou shalt not compromise the 1420 operation, right, with your 408 system. So he optimizes at 1420, adds probes which will work at 408, produces either right or left-hand polarization. Right, and let's see how he did. Here are the antenna patterns at 1420. with and without the probes. And you can see that the 1420 are not compromised in any way. And here's the pattern. These red lines are the rim of the dish as subtended from the focus cabin. So it's going to be okay. The asymmetry here is caused by reflections in the test range, which are unavoidable. Okay, but the other half of the problem is a similar one to the LO for the 1420. So control, here's a master back here at 204. VCO, etc. signals go along a cable which is buried here and slave this VCO in the focus box for the mixer to a master back here. But there's only one cable. There are 3 buried cables along the tracks, 2 of which have been used, so there's 1. So he has to get his IF back, and he has the realization, I could make the IF phase independent of cable length too. Let's try it. Well, make a long story short, it does work, and he achieves a 1/10 of a degree phase stability in the IF phase at the correlator, even though the cable length changes by 2 centimeters. But the ultimate test, of course, is to make an image. So, 7-degree field of view, 3.5 arc minute synthesized beam at 408. This is the first image of a faint supernova remnant, HB3, this is W3, W4. First high-res image below 2.7 gigahertz. Success. Meanwhile, back in Edmonton, life goes on. Just to remind you what Campus Lake was like in the 80s. You don't remember that? Okay. We have a research associate, Graham Walker. Good thing, because HIA, DRAO, offers us a contract to build a 2-channel cooled gas jet receiver for the 26-meter. And it's going to use a closed cycle helium cryostat. The previous receiver on the 26-meter out here had these specs: 50K noise, 17 dB gain, bandwidth 60 megahertz. This is what Graham achieves: 6 times the bandwidth, half the noise temperature, where are we here, and 50 times the gain. Right, and it looks like that. And there it is in the focus box, which is up there. And the first thing John Galt does is look at Comet Halley, OH emission, and he tracks it for about 6 months. Now that's a very small optical depth, maximum intended temperature of 0.07 Kelvin, so it works. DRAO also offers us a contract to build low noise amplifiers for the synthesis telescope. Right, 4 dishes, 2 each for right and left hand circular polarization. With 2 spares, that's 10 LNAs. Meanwhile, there's a visit from Tom Legg in Ottawa. Tom would like to build, he's had this idea, of course, Tom had ideas, a focal plane receiver, array receiver for the JCMT. Here's the idea. Why not, he says, integrate superconducting mixers onto planar quartz substrates, put them in here 4 across, 3 layers deep, sandwiched between these metal things, so that here are 12 beams coming in from the telescope at, say, 345 gigahertz, producing 12 4 gigahertz outputs. Why not fabricate them using IC planar technology instead of expensive and difficult machining and electroforming? Right. So, luckily, the Alberta Microelectronics Center is directly adjacent to campus, and we have a new faculty member, Mike Brett, who has close ties with them. Here's a research associate, Ken Westra, at the sputtering machine. We start in niobium nitride, some problems, switch to niobium, Ken goes off to Britain. We get a new research associate, Kevin Cornelson, and Bruce Veit 2.0, 3.0. He's been off in Pasadena working with Tom Phillips. Right, so Bruce is doing his PhD now at millimeter waves or sub-millimeter. These are the steps that you need to do to actually produce one of these modules, etc. You end up dicing these quartz wafers. You get up to 28 modules per. And then you have a whole bunch of testing to do, including noise temperatures, antenna patterns. Meanwhile, in Ottawa, design is underway. A lot of testing underway by Tom Legg and Morley Bell, but the fabrication is always done at AMC next to U of A. So here's Kevin. Here's a 345 gigahertz source, Teflon lens, a Mylar diplexer, so it's reflective to a few percent. The 345 enters a Mylar window into the cryostat, and the signal comes in the other route. Okay, that's an example. Meanwhile, back at Dreo, changes to the synthesis telescope are underway. Okay. The telescope is going to expand from 4 to 7 antennas. It's desired to double the bandwidth from 15 to 30 megahertz. And the scientists would like to have the polarization, the capability of doing polarization imaging. But the guy doing the correlator design is David Karpa. The actual polarization imaging will be somebody else's problem. Okay, here's what he achieves. Gray hairs all around. It was a difficult project. The correlator he is replacing is this one. What he achieves is the ability to handle 21 simultaneous spacings, or interferometers, so that a survey, instead of taking 35 days, takes 12 days. The bandwidth doubles. There's root 2 and signal to noise. The correlation efficiency goes from 0.8 to essentially 1. You're oversampling and you have finer quantization. There's another 20%. Polarization imaging becomes feasible. You see that in a second. And there's built-in self-test. Details upon request. Right. Next thing is to implement the polarization imaging. Rick Smeagol, some of you know him, very inventive guy. Here's our DA 530 supernova remnant again, imaged by Roger and Costain. In the interim, it's been found that this SNR is highly polarized. People were talking about 14, 15%. This is polarized up to 50% in spots, as seen at 4 arc-minute resolution. Right, so it's going to be a good test object. It's size 27 arc-minutes, so it's a good test object. The problem being, for Rick, that the antennas are nominally right and left-hand circularly polarized, but in reality, there's a leakage, or could be, between the hands of polarization in the feed antennas, whatever. So here he sets out to measure the polarization properties of the feed horns that Bruce introduced earlier. And he finds, in fact, that they do leak right into left, left into right to some degree anyway. Also in this telescope, with equatorial mount, it's very difficult to separate the instrumental polarization from that of the source, because you cannot change the parallactic angle, and an Altaz mount, like at the VLA, does it automatically. Whatever. Okay, so Rick has to invent some calibration procedures. This is standard calibration for intensity imaging, eye imaging. If he corrects for the non-orthogonality, the leakage, then by calibrating, observing calibrating sources and applying corrections such that the spurious, if you like, polarization goes to essentially zero, he finds that he's reducing the errors by, he can achieve about an order of magnitude 10 times reduction in his leakage, and he thinks that's going to be enough to make good images. Okay, my ellipses are all over the place. Anyway, there's a further stage he could do, but the antenna test range has reflections that are too bad. Whatever. Let's test this idea that he can do level 2 correction. So he does image this DA530. These polarization vectors look very much like what the VLA finds, what Effelsberg finds. Conclusion, it's working. He then makes another observation with this object set off the field of view center by 30 arc minutes. Conclusion, because this thing is 27 or 30 arc minutes wide, the field of view for polarization imaging is at least 1.5 degrees. Great. Okay, we're back where we started. I would just like you to notice one thing. These asterisks are projects that were supervised here on site by Tom Landecker. Okay, rather important, 4 minutes. So here he is. Sorry, Tom, it's going to be embarrassing. Many personnel over the years have helped an awful lot. Every student that's ever spent any time here comes away really impressed and really grateful. But the go-to guy has always been Tom. Co-supervised many theses in loco parentis, in good times and bad, huge knowledge, deep, broad, etc. And he's become an adjunct prof in our department so that he can get NSERC operating money to help them with their travel and their living expenses. Also, as I was talking to Gary about, the students build prototypes. The people here, the professionals, have to turn it into reliable, calibrated, etc. hardware and software. A totally different dimension to our interaction over the years is that we've got to look at the data, right? So we've had the opportunity to look at galactic objects and their interaction with the ISM. And notice again, 5 of these 7 objects have been collaborated with Tom Landecker. And that's the end. Oh, also, every image there and all the channels of H1 data, etc., have been processed using Dreo software. Initially here, but later using the Dreo export package. What a terrific bunch of guys and women. Just a fabulous bunch of people to work with. I think that's it. And the time, I'm out by.
Questions for David?
Just in case you're wondering, we are appreciated back home on campus.
Oh, wow.
Yes. Yes, Joe.
Yeah, I have an interesting comment on Tom Lang's stuff.
Yes.
When I came back from Hawaii, Tom had bought himself a copy of AutoCAD, but he couldn't figure out how the hell to use it. So
Yeah.
I've been doing AutoCAD stuff for years, and I was now retired. So Tom talked me into helping him out. So I did all the AutoCAD drawings, but I never knew that they were actually produced.
Yep.
But the thing about it was that Tom would change his mind about every 3 days. It took about 3 months to do those drawings.
Yeah.
Yeah. And there was a lot of restrictions on what you could do because all the sides had to match and they all had to be a certain length. So every time he changed his mind, I'd have to go back and recalculate everything.
That's the price of genius, I guess.
But it actually did get produced, eh?
Oh, absolutely.
Oh, well, that's good to know.
Yeah. Phil.
Yeah, I was just going to comment that in the mid-'80s, Katie Kim, who came here from Toronto, was my student for about a year or so.
He liked opera, right?
He did, that's right. He sang in a chorus.
He sang in the hallway here.
Oh, I see. Okay. Anyway, one of the things that I suggested you do was to outfit the interferometer here for polarization at 408 megahertz. And he had to start at it, and I could tell that it was just one more project for him, and he was a very productive student. But I didn't want to
Bruce, are you here? Comments on your probes at 408 for polarization? They're still in use, by the way.
so are we talking about the probes that I...
No, the probes that Bruce put in for the 408 conversion of the feeds from single frequency 1420 to dual frequency.
Did this happen when Katie Kim was here?
It happened before that, but they were in use continually after Bruce. I think there are some asymmetry problems, and I think the cross-handedness would be a real problem.
Well, yeah, it was just too complicated for
Okay.
KT for yet another fifth or sixth project to tuck under his PhD. So we pulled the plug on that one. But I'm not sure if there was any interaction with what you were doing there. Probably not.
The correlator, by the way, has to handle not just left, right, but left, right, and right, left. So it needs many more channels to process, to do, as you would well know from Jodrell Bank. Yeah, okay.
David and I have been in touch, Ellen and I have been in touch about Winglow's thesis. Somewhere in the archive, I'm sure there's a how much and how long it took, but Reber received a copy of Bruce's thesis and Winglow's thesis, was really, really impressed by both of them. Yeah. The letters are in the
There are letters on file from Reber saying, I've seen many PhD theses with far less in them. So several hundred milli-Kronbergs. No, I'm talking about you and Bruce and Winglow. Yeah, yeah.
All right. Any other questions? We have one more minute. All right. Well, let's thank David again.
Okay.